Hello and welcome to this video on evaluating and graphing piecewise functions. We will first talk about just observing the different qualities of piecewise functions. We see two examples in front of us right now on the left and right, where in general you know piecewise functions because they're not a straight line, a linear function with all one connected piece. Where in the case of the one on the left, you have two pieces, the bottom left piece and the top right piece. They are connected, but they are in fact two different pieces with two different slopes. And then more so on the right, where you have a line and they're graphed in pieces, where you'd have a function that represents each of these two pieces, but the two pieces have different domains. The x values that they are being used for are different. You might say the one on the left, well, this is for the x's that are less than this value right here, and the function at the bottom would be for the x's bigger than that same x value. You also will notice that you have an open circle and a closed circle here. When you have these open circles, that is going to represent either less than signs or greater than signs, depending on which way you go in these piecewise functions. In this case, this would be a less than sign for this open circle. For closed circles, such as this one, that's going to represent functions that have either less than or equal to or greater than or equal to signs in your functions. When you have either one of these, you are starting at a number and including it, and then either going up or down from there. If we continue on into these examples, sometimes there are multiple different pieces. In part 9, we have 3 different functions, a left function, a horizontal function, and then a right function, and they could still all be connected to each other. The one on the left has 3 different functions where you have them being all disconnected from each other. Something to keep in mind is I mentioned the word function. Something can only be a function if for every single x value, there's only one y value. And that is usually known as being tested by the vertical line test. If I can draw a vertical line through a function like this one right here, well, I would know it only hits my function if there's one place. And that means it's a function, this x value only has one y value. And so it's important to note that you don't want any overlapping functions because that would make it not a function at all. And then you can't say that it is a piecewise function from there. Something to pay close attention to is if you have functions where you have an open circle and closed circle vertically aligned with each other, like so, well, that is still a function. When you have an open circle, we're not including this value. We're including the filled in circle instead. Same thing goes for the part right here. We would only include the closed circle, so this still remains a function. And then lastly, you might see a very different sort of function like in number 10. This is known as a step graph because it kind of looks like a pair of stairs or some steps. And that is a very common thing to see modeling something in the real world. And that would be used in statistics most of all. We're now going to move on to the most important part of this video, and that is going to be evaluating and graphing piecewise functions. And along the way, we'll see if each of these piecewise functions are functions or if they are not. So in this first example, we have a function where part 1 is x plus 5 when x is less than negative 2. And negative 2x minus 1 is the function when x is greater than or equal to negative 2. So mainly what we want to do first is try to think about how we would evaluate these. So evaluating is very straightforward. We just look at this x value, 3. That is our input. So we just need to think about, is 3 going to be less than negative 2, or is 3 greater than or equal to negative 2? Well, 3 is definitely that second one. So we would use the second equation since 3 is greater than or equal to negative 2. And I can just plug that right into x and evaluate negative 2 times 3 minus 1 is equal to negative 7. Same thing with number 2. If my input is negative 4 for x, negative 4 is less than or equal to negative 2, so I use my first equation, meaning I would do negative 4 plus 5 is equal to 1. And so f of negative 4 would equal 1. Now f of negative 2 is my input, and this is a little tricky because we have to make sure is negative 2 f of negative 2 is a little tricky. We have to think about if negative 2 is less than negative 2 or greater than or equal to negative 2. And you just have to think about what those symbols mean. Negative 2 is definitely equal to negative 2, so it fits the second version. And I would do negative 2 times negative 2 minus 1, which ends up being equal to 3. So that is the basics right there already of being able to evaluate a piecewise function. Now let's look at trying to graph it. I find the easiest way to graph is try to use these important numbers in your inequalities and use those to get one of those, the open circle or closed circle numbers, and then graph the line from there using our linear equation skills. So if negative 2 is the border number here, I'm just going to plug negative 2 into x. So that would mean I would have the point negative 2, and then if I put negative 2 into x, negative 2 plus 5 is going to be equal to 3. So since I have a less than sign, that is going to be an open circle. So let's go to negative 2 comma 3. And I'm going to draw an open circle right there. Now for my second equation, I'm going to use negative 2 and put that into x. So that would still be at negative 2. And when I put negative 2 in here, we already know from earlier that that is equal to 3. So sometimes this will happen where your open circles and closed circles are on the same point and kind of just working together at that same place. So if we want to try to graph this, we just need to follow the point. So if we need to draw a line, all we really need to know is we have one point already. We just need one more point to be able to graph a line. So for the blue graph, I could think about, well, I just need to try another x that's bigger than negative 2. So I could try 0. So if I put 0 into x, well, that means negative 2 times 0 minus 1 equals negative 1. So 0, negative 1 would be my next point. So 0, negative 1 is down here. I could also just follow the slope down to and over 1 to make that point. And so that means that this would go down like so, with an arrow on the end. Now for the red graph, I have basically to pick a point lower than negative 2, so I could pick negative 4. Well, negative 4 plus 5 is negative 1. So negative 4 comma 1 will be right here. And my slope is also just a 1, so I could just go down 1 and left 1 as well. And I'm just going to draw my line through those points. And I have a fairly accurate picture of what my graph would look like in graphing this function. We're now on question number 3. And in this example, we are going to be graphing two functions again and the inequalities that go along with it as well. So let's evaluate our function first and then work on graphing it second. So in this first function notation problem, we have f of negative 4. Well, negative 4 is definitely less than 2, so I would want to use our first equation. So it would be like negative 4 over 3, which would basically become 4/3, plus 4. And we can just grab a calculator and do 4/3 plus 4 and get 5 1/3, or about 5.33. In problem 2, we need to evaluate our function at x equals 8. 8 fits into the second one, because 8 is greater than or equal to 2. So I just need to put 4 times 8 minus 2, and 4 times 8 minus 2 is equal to 30. And lastly, we are going to use 2 as our final input. 2 is not less than 2, but 2 is greater than or equal to 2. So it would fit into our second equation. And we would do 4 times 2 minus 2, and that would end up equaling 6. We've now evaluated, so let's work on graphing our two equations. And we want to start with our border numbers first. So since I have a 2 here, I'm going to put a 2 into this x right here and do negative 2/3 plus 4. Negative 2/3 plus 4 is going to be equal to 3.33. So I would have 2 comma 3.33, and that is going to be an open circle because of that less than sign. And we can go over to 2 comma 3.33 and put a little open circle right there. But because of that 3.33, we're going to have to look for other points that we can graph. But we'll come back to that in just a moment. For equation number 2, I need to look at x is greater than or equal to 2. So the 2 is going to go into x. And we can just use what I already found at the bottom. I know that's going to be 2, and I get a 6 out of that. So, and that is going to be a closed circle because it's a greater than or equal to sign. So that's closed. And so we can go over to 2 comma 6 all the way up here and put a closed circle right there. So let's think about how we might graph this from there. Is that we need to try to look for some more points. Now the second equation, the purple one, is going to be a little bit easier. We just need to go off of our graph a little bit because our slope of this equation is 4, meaning that we'd have to go up 1, 2, 3, 4 spaces and over by 1 space to make our line look like something like that purple one right there. So we have that purple graph done, but now we need to work on the blue one. So we know we have 2 comma 3.33, which we can't really use. But in this equation, we also see that the y-intercept is going to be a 4. So I could put a solid point at 4 right there, and I could follow my slope of negative 1/3, going up 1 and left 1, 2, 3. So I have a second point right there, and all I need to do is just draw my function through all of those points. So if you can't use the point that you're given from these border numbers because of decimals, just look at the linear equation itself and see if you can plot it using the slope and or the y-intercept. Now, if I wanted to decide if this is a function or not, I just need to look at my graph. The whole blue part, I can draw a line through all of that. No x has more than one y. Same with the purple. And we just need to look at this intersection point right here where I can draw a nice green dotted line. Well, I know that I have an open circle right here, and a closed circle right here. So it's not failing the vertical line test because I'm kind of ignoring the open circle. I'm not counting that as a point because we only cared about, for the blue, less than 2, not equal to 2 at all. So we would just only worry about the solid pink dot that we saw earlier, part of that pink graph. So I would say that yes, we have no overlapping points other than a closed and open circle overlapping each other, which is actually okay to have. We are going to finish this problem set with number 4 on this particular worksheet and evaluate and graph this piecewise function because it looks a little different. First, it has 3 different functions. So we'll have 3 different pieces of this graph. And second, it has a part of it where it's just a number. So let's start by evaluating. That is generally the more straightforward part. So -2, if we look at our inequalities, -2 fits into the first inequality because it is less than or equal to 0. So I would do -2 plus 4 is equal to actually 2 plus 4 instead of that, and that would end up being equal to 6. Next, I'm looking at 0. 0 would also fit into the first equation because it is equal to 0. It can't fit in the second one because that x value, which is 0, isn't greater than 0 or less than or equal to 5. It's the or equal to part of the first equation. So I would have -0 plus 4, which is just going to be 4. And lastly, the third evaluating problem, we're trying to see what would happen if at 5. So this is another tricky one because that's 5 is one of those border numbers. 5 would fit into the middle inequality because 5 is less than or equal to 5. It is not greater than 5. So that means we would do 2/3 being multiplied by 5, and then -1. If we grab a calculator, that would end up being equal to 2.33. The problem is not up here, but something we want to consider really quick is this final equation down here. We say we were asked a couple different questions. Say we were asked, use a different color. Say we were asked something like f of 3. No, not f of 3. We want to use instead f of 6 and then f of 10. So both of those x values fit into our third inequality. They are both greater than 5. But the y value here, which is this is f of x equal to 2 down here, it would just be 2. So no matter what this x value is, as long as it is bigger than 5, it is always going to be equal to 2. And that's something to file away as something you might see in problems in the future. Now let's get into graphing. So let's graph our first equation first. So 0 is our border number. Put that into x. We already know it's equal to 4. So 0, 4 is our important point, and it is going to be closed for sure because of that less than or equal to sign. So 0, 4 is right here. And we know it's going to be less than, so we can follow our slope of -1, up 1 and left 1, up 1, left 1, up 1, left 1. And we have a little arrow on the end. It's going to keep going that direction. Moving to function number 2, we have 0 and 5 as our border numbers. So we need to get both of those. So if I put a 0 into my equation, that would end up with 0, -1. And that's going to be open because of this less than sign. So 0, -1 is going to be an open circle. And our second point, 5, if I put it in, we already know what that equals, 2.33. So I can plot the point 5, 2.33. And that would go over here to 1, 2, 3, 4, 5, and then up to about right there with a closed circle. And the good thing is, since we have both endpoints, we can just connect these two dots, making this function pretty straightforward. And finally, our third function, since that y or f of x is just equal to 2, whenever you see that happening with just y equals a number, that's always a flat horizontal line. So it starts at 5. Well, so we can basically put an open circle at 5, comma 2. Open circle because of this greater than sign. And let's plot that point. So we have at 2, 5 right there. And then we have just a flat line going to the right since its x is greater than 5. And we have that as our graph right there. So that covered lots of good examples of graphing piecewise functions as well as evaluating them. Both are very closely related to each other. You have to kind of do one when you're doing the other. And just as a final note, for whether this is a function or not, we can draw vertical lines right here through a close and an open circle, so that's all good. And then again right here through a close and open circle, so that is good as well. And this final one is definitely a function. So we've now covered completely evaluating and graphing piecewise functions. Thank you for watching.